Okay, thank you for all participants. And then we have now the second lecture by Pascal about introduction to few body physics. So Pascal, please go.
Thank you very much. Yeah, so maybe I should just remind you what we saw in the previous lesson. Yes, that was the summary. So in the previous lesson, what we looked at the concept of zero-range universality at the two-body level. So we saw that when we have a pairwise attraction between two particles, at the point where the S-wave bound state appears, there's this universal regions which are described by a single parameter, which is the scattering length, and that can be described by a so-called zero-range theory, which is parameterized only by this single parameter, the scattering length. And then we saw that there are a few examples in nature, and that can also be engineered in the laboratory. And so what we're going to see in today's lesson is what happens when we go from two-body to three-body. So let me go back to yes. And so I chose to follow some kind of a historical approach about how this three-body universal three-body physics was understood as time developed. So I will start with something called the Thomas collapse. Then I will discuss the so-called Skorniakov Ter-Martirosian equations, and this will introduce the work of Vitaly Efimov, which led to the understanding of the Efimov effect and the Efimov states, which I will then describe in detail. So let's start with the Thomas collapse. So that was back in 1935. And so at that time, Llewellyn Thomas was studying the basic properties of nucleons and looking at a interaction between neutrons and proton and structural H3. And so, he looked at systems like deuteron made of proton and neutron, or the triton made of a proton and two neutrons. And so that was the still early days at the time. So the knowledge of nuclear physics was not as accurate as it is now. So in his work, Thomas described the system by just a single interaction between the protons and the neutrons. And so in his work, the Hamiltonian of the system were described by this. So here, this is the two-body Hamiltonian with the two kinetic terms, and this is the interaction V between the neutron and proton. And then for the triton, that was described by this Hamiltonian with the three kinetic energies and the two interactions between the neutrons and the proton. And he looked at the ground state energy of the system. So this can be calculated for the two-body system. For the three-body system, it's a little bit more complicated, as you can imagine. But one can use the variational principle, which tells that the ground state energy of a quantum system is always smaller than the average of the Hamiltonian in any state that you can choose. So that's as you know, very powerful principle. And if we can find some approximate ansatz for a wave function that is good enough, it may approach this this boundary, the true ground state energy, sufficiently. So he just came up with a complicated ansatz to describe this three-body system. And what he found is that when calculating the average of the three-body Hamiltonian for this particular ansatz, he found that the energy he found was proportional to the two-body energy, two-body ground state energy, times 1 over b squared. So b is the, as I recall, this is the notation I use for the range of these potentials. This was a kind of intriguing result because it means that when, if we consider zero range potentials, when we take the limit when b goes to 0, as I showed you in the previous lesson, this is a well-defined limit. In the two-body case, we can have a vanishingly small range of the potential, and yet fixed two-body scattering lengths that fixes all the physical properties of the system. But in this case of this three-body system, when one takes a zero-range limit, the energy, the ground state energy, actually has to go to -infinity. And it was not clear why there was such strange properties for three-body systems. And so this has been called the Thomas collapse. But nonetheless, with this result, Thomas was able to get an estimate of the range of the nuclear forces, which was not so well known at the time. And from the known ratio of the experimental values for this triton and deuteron energy, which is about 4, he concluded that the range of the nuclear forces should be about 6 femtometers, which is maybe a little bit some kind of overestimate. But essentially, that's the right order of magnitude. So, okay, that was one of the earliest results for this three-body system in the context of zero-range limit. And that was a kind of mystery at the time. And then many years after that, two Russian physicists, Skorniakov and Ter-Martirosian, looked again at this problem, three-body problem, with short-range forces. So, namely, they applied the zero-range theory that we saw in the previous lesson to this three-body problem. So let me sketch out how they did it. So now we have a three-body problem. So we have a wave function that depends on three coordinates, three-dimensional coordinates, x1, x2, x3. And we can write the Hamiltonian like so. So we have the kinetic energy operators for each particle. And then we have, so we assume that we have pairwise interactions. That depends on the distance r12, r13, and r23. So the first thing, of course, is to, because this is a translationally invariant system, we can eliminate the center of mass. And then we can express the remaining coordinates as two coordinates, which are called the Jacobi coordinates. And so they are essentially the relative vector between two particles, and then the relative vector between this pair, the center of mass of this pair of particles, and the third particle. So as you can see, there are actually three possible choices of such coordinates. So, so these are the so-called the three sets of Jacobi coordinates, and this is how they are related to the original coordinates of the particles. Then, if one, so after these treatments, the Hamiltonian has the following expression. So now we have the kinetic energies related to these two Jacobi coordinates. So we just choose a particular set, for example, this one, and then we have this expression for the kinetic energies, and then we still have the interaction potentials, whose arguments there can be expressed in terms of these two Jacobi coordinates. The Schrödinger equation looks like this at a particular energy E. And we're interested in the solutions at negative energies. We're interested in bound states. So now we apply the zero-range theory. So as you remember, the zero-range theory can be implemented using the so-called Bethe-Pyers condition. And here I choose the form of this condition when it is actually directly implemented in the Schrödinger equation itself. So that means that we don't have a free wave equation, but we have a free wave equation with some source terms that are delta functions for each interaction, for each pair of particles. So as you remember in the first lesson, there's a prefactor in front of this source in terms of these direct delta functions. And now these prefactors, they depend on the remaining Jacobi coordinates. So if we have the pair 2, 3, for example, this quantity here now depends on the remaining capital R1 Jacobi coordinates. And the same occurs for the other terms. And to apply to complete this condition, we have to impose that these prefactors here are actually related to the form of the wave function when two of the particles come close to one another. So when the distance between particle I and j goes to 0, the wave function factorizes as 1 over this distance minus 1 over the corresponding scattering lengths between these two particles times a factor that depends on the remaining Jacobi coordinates rk. And these are the factors that appear here in front of the of this delta function. So this is just the application of what we saw in the two-body theory, but now in the three-body systems we have this new dependence on the extra Jacobi coordinates. Then the next step, which is natural, is to go to momentum representation. And the reason is because in momentum representation, these kinetic energy operators, they actually become numbers, as you know. That's a generic property of Fourier representation. So usually the interaction terms, they would become non-local complicated integrals in momentum representation. But in the case of the zero-range theory, as we've seen, they actually remain very simple because the Fourier transform of a Dirac delta function is just 1. So it's indeed interesting to go into this momentum representation. For these negative energy states, we can simply invert this equation and find the expression for the wave function in momentum representation is like this. So here, this capital P and small p, they are simply the Fourier conjugates of the Jacobi coordinates capital R and small r. Okay, so now we have the expression for the wave function, but what we don't know is these factors. So this f tilde are simply the Fourier transform of this f of capital R. So what we need to do is to now apply this Bethe-Pyers condition, but in momentum representation. And that we have seen in the previous lesson. And when we combine these two equations, we end up with an equation that determines this prefactor f. So this is just an equation on f. And it has this form, this final form. So you see, this is an integral equation. So we started from a differential equation, but in the end, we get an equivalent equation that is that has no derivatives, but instead has an integral. So this is an integral equation. And you can see here the benefit of this zero-range theory. Because we could we could simplify the interaction with this kind of contact terms. The benefit that we gain is that now, instead of having an equation on a function of two three-dimensional quantities, we end up with an equation on a function of just one three-dimensional quantity. So this is a huge simplification that makes it much easier to solve numerically and even analytically, as we will see. And as I mentioned in the first lesson, this is not just a property of zero-range theory. This you can get for any separable interaction. And this zero-range contact interaction, they are just a particular case of separable interactions. But for the moment, we'll just use this, this zero-range theory. So here I give you the actual derivation of the equation, which is quite simple. Actually, we don't, here I just reproduce the demonstration I did in the first lesson, so we don't need to read this. If you remember the first lesson, we've seen that this boundary condition in coordinate representation can be written like so in momentum representation. So the integral over the relative wave wave vector between two particles of the wave function minus this quantity f divided by this relative wave number squared. This integral is simply equals to -1 over the corresponding scattering lengths between these particles I and j times this factor f. So this is the momentum representation of this boundary condition. So now we can combine the expression for the wave function, which simply insert this expression into this integral here. So we get this. And we see that among these three terms, one of them is actually the same as the one on the right-hand side. So we can put it away. And I think wait a second. Yeah, okay, sorry. For the moment, we keep this term here, and then we just combine, there is this term here, which is the same as this one here. So we put them away, and here we have an integral that we have encountered before. This is an integral over the wave vector p. And the only thing, the only parameters that enters in this integral is this quantity here, 3/4 capital P squared plus kappa squared, right? You know, kappa is related to the binding energy of the that we are looking for. And you can convince yourself, we've seen that before in the first lesson, that this integral is actually equal to the square root, it's proportional to the square root of this argument. And that's something you can find easily from dimensional analysis. Here you have a 1 over a length cube, and here you have a 1 over length squared. So in total, this is proportional to 1 over length. So in order to construct 1 over length from this quantity, you have to take the square root. So then we put the right-hand side on the here on the left, because as I mentioned, that this is the same term here. So we get this prefactor, and then we get these two remaining integrals. And finally, these two integrals we can treat. You see, the issue in this integral is that we integrate over the relative wave vector between I and j, but the function f itself is a function of this other Jacobi wave vector. And so one can find the relations between these different Jacobi wave vectors. This is something that you can you can write directly, or you can find from the original definition of the Jacobi coordinates in real space, and taking the Fourier conjugates. So you can find such kind of linear relations. And then you see that you can actually change the variables in these integrals from pj to this argument of these functions. So making this replacement, this pij here in these denominators are replaced by these expressions. And now we can integrate over capital Pi. And then the last thing that we can do is just relabel this Pi and Pj as some wave vector Q, and then we end up with the Skorniakov Ter-Martirosian equation. Okay, so once we have this equation, we can apply it to the problem of few-nucleons, and so this is what the Skorniakov and Ter-Martirosian did. And actually, as you probably know, the nucleon interaction depends on the structure of these nucleons, in particular their spin arrangement. So these nucleons have a spin 1/2, and they can be arranged in their spins can be arranged in either singlet, which is the antisymmetric configuration, or the triplet configuration, which is the symmetric configuration. And depending on this configuration, the actual scattering length between the proton and neutron is different. So in the case of the singlet case, we get large negative value, -23 femtometers. And in the case of triplet, it's about 5 femtometers, a positive value. And so then the authors look at the problem of deuteron-neutron scatterings, and then there can be two different possibilities depending on the spin configurations. So the first one is when the total spin of this three-body system is 3/2. And in this case, you see that what will intervene is the triplet scattering lengths between the neutron and protons. Whereas the other possibility, when the total spin is 1/2, then we will have at the same time the triplet scattering lengths and the singlet scattering lengths entering the problem. So in the first case, you can convince yourself that due to the spin configuration and due to the fact that that we have a fermionic symmetry, from the fermionic symmetry under the exchange of identical particles, for example, like these two fermions, we can show that the symmetry of the total three-body wave function is such that the components f follow this have this structure. So f3 is equal to -f2, which we call simply f, and f1 equals 0. This is something that you can derive simply by exchanging these two neutrons. So the the Skorniakov Ter-Martirosian equation, the general form I showed before, reduces to this particular case. So now we have only one term here. And this equation can be solved. You can solve it numerically. And this is what they did. And they found from this equation that you can relate this f to the neutron-deuteron scattering length. If you look at the form of the momentum expression of this function, you can extract this neutron-deuteron scattering length. And they found that the scattering length is about 1.2 times this triplet scattering length, which is the only length scale that actually enters the problem here. So this is actually a universal result. So in this zero-range theory, there's only one length scale, and we get, as a result, a universal result for this scattering length between this dimer, this pair of nucleons, and another nucleon. And then they tried to apply the same formalism to this configuration. But I think they obtained some numerical results. But it turns out that that numerical result was actually kind of arbitrary result. That was not converged result. And I think they were not aware of it at the time. Here I'm showing a simplified version of this case. This is when the triplet scattering length is equal to the singlet scattering length, which is of course not true in reality, but that's just to show you the issue that occurs in this kind of problem. In the simplified version, this is equivalent to the problem of three identical bosons. If you assume that you have three identical bosons, then you will find exactly the same equation, because that corresponds to a fully symmetric spatial wave function. And in which case, F1 is equal to F2 is equal to F3. This is which we can just call F. So you end up with this equation. It's very similar to this one, right? The only difference is that instead of a minus sign here, we have a plus sign and a factor of 2. But apart from that, it has the same structure. And now it turns out that this equation behaves very differently from this one. So, and the problem, as it was found, is that the energy of this for this equation is not bound from below, and of course this is related to the Thomas collapse that we saw before. So this was actually realized in detail by Minlos and Faddeev a few years after, because they actually found an analytical solution to this Skorniakov Ter-Martirosian equation, which is quite remarkable. So to find this solution, they considered again the particular case when of this Skorniakov Ter-Martirosian equation for the simplified case of three bosons. So, and then at unitarity, so that means the scattering length goes to infinity. So here this term disappears. We set A to infinity. So then we get this equation. So again, this kappa here is related to the energy of the system. This is the binding wave number for the system. So let me show how they could actually find an analytical solution. The first step is to extend the definition of this function and this integral to minus infinity. So you just assume that these functions are even, and then you can convince yourself that this integrand here is even if you change q into minus q. You will not change these terms. You will switch the signs here, which means that you will get a minus sign for this logarithm that will cancel with the minus sign coming from this minus q. So you can just easily extend to minus infinity by removing the factor of 2 here. And then the crucial step, the second step, which is crucial, is to make this a special change of variables that is non-trivial. I don't know how they could find this particular change of variables, but if you make this change of variables, so this is so now you express these wave numbers p and q in terms of a new variable z and z prime, and you introduce this length scale kappa. That's the binding wave number that you're looking for. And if you make this change of variable, this is the magic of this change of variables, is that actually you can remove the kappa from this equation. So that's something that you can check for yourself. But if you make this change of variable, you get this equation in terms of z and z prime. And here we have these new functions g of z, which are given by z squared minus 1 over z squared times the original function f that we're looking for. So already you can see that some magic has happened here, because we were able to eliminate the energy from this equation. So it doesn't depend on the energy anymore. But we can go further and actually find an analytical solution. The property that is related to this absence of energy is that now there's no scale in this equation, and it is actually scale invariant. So that means that if g of z is a solution, then g of lambda z is also a solution. That's something that you can check very easily if you make this change of variables here. You replace z by lambda z. Obviously, that will not affect this ratio, and that will not affect this ratio either. So indeed, g of lambda z is also a solution of the same equation. So then you can look for solutions of this form. When you have something that is scale invariant, you can look for solutions that are power laws like this. So z to some power s. So if you make this replacement, then you find, so you have z to the power s here, and also here z to the power z prime to the power s minus 1, if you divide by the z prime. And then you can divide the whole equation by z to the power s, so you get minus 1 here. And then you can introduce x or x prime, which is z over z prime over z. Sorry, there shouldn't be any prime, sorry, here. This is just x is equal to z prime over z. So then you have some integral here. That is non-trivial, but somehow they were able to calculate this integral. If you don't believe, you can check with Mathematica or something like that. And you find that it's actually expressed in terms of sine and cosine functions of this parameter s, this exponent s, satisfying this condition. So then from this equation, we get a transcendental equation for the value of s. So we can look for its solutions. So there are two kinds of solutions, the real solutions and imaginary solutions. So what I did here is I plotted this function, the function of s, the norm of s, and this line here is just the function s. So whenever these two curves intersects, then we have solutions. So we have real solutions, and it turns out we also have one imaginary solution, or I should say two imaginary solutions, s equal plus or minus I S0, which turns out to be very close to 1. It's 1.00624, etc. So then we can consider this particular solution, this imaginary solution. And then, so we can express g of z as a linear combination of these two solutions, so z to the power I S0 and to the power minus I S0. And since g of z is originally defined like so, it means that g of 1 has to be 0 because these two terms cancel. So therefore, these two coefficients here must be opposite. So we just call it C. And so we have this form. And now if we go back to the original variables, the physical variables, the wave numbers, we get the expression for f, which is this way. So that's interesting. They could actually work out the full analytical solution. But in any case, we saw right from when they made this change of variable that the final solution is actually valid for any value of k, because k actually disappears as we derive the solution. And so that means any negative energy. Remember k, sorry, not k, kappa. Kappa is the binding wave number, so associated to a negative energy. And this can be as large as we want. And this is actually consistent with the Thomas collapse. That's just a kind of confirmation or rediscovery of the Thomas collapse. So, so obviously something is wrong from the physical point of view, because we cannot have infinitely negative energies. So it means that somehow there's something wrong about the model. But it was not, even when the people could derive this analytical results, it was not really clear what was wrong. People thought that maybe physically something is missing, that we should probably introduce some new physical parameter, and in order to renormalize this naive theory and produce some physical results. And that's true, as we will see. But essentially, people were expecting to have essentially just one bounce, three-body bounce state, and try to fit this three-body bounce state to what was known, what they had in mind, the Triton. And then a few years later, there came the work from Vitaly Efimov, and that clarified a lot of this about these issues. So his findings were published in these papers in early 1970s. And so let's see exactly what Vitaly Efimov did in his paper. So I will follow very closely the derivation that is done in the original paper by Vitaly Efimov. So actually the interesting thing is that he did not solve the problem in momentum representation. That seemed to be the most advantageous representation, as I showed you. But as we will see, actually, if we stay in the position representation, we will actually gain some insight about what happens in the system. So now we start again, we solve again the same problem, but now in coordinate representation. So again, we have the Hamiltonian. So now we just use the free Hamiltonian, and we impose this beta bias boundary condition for each pair of particles. So again, I'm considering for simplicity, just the three boson problem. So with a completely symmetric wave function. So as we've seen, we can eliminate the center of mass and express this in terms of the Jacobi coordinates. But here I will make a slight change of definition. For the Jacobi coordinates between this pair and the third particle, I will introduce this factor square root of 3/2. And this is just a definition. And this is just a convenience so that the results look better and actually look better in this coordinate representation. For instance, what you can see immediately is that if you make this kind of choice, then when you express the Schrödinger equation in these two coordinates, you get the Laplace operators for these two coordinates with the same prefactor. If we just use the previous notation, which is capital R, we would get the Laplace operators for capital R, but with a prefactor 3/4, as you may remember from the previous slides. And so with this, that makes the notation a bit more symmetric and easier to deal with. So this is what the Schrödinger equation looks like now with these coordinates. And then one can make the so-called Faddeev decomposition. So one writes the wave function as a sum of three terms, like so. So a function of the Jacobi coordinates for the three different sets. So at first it might look a little bit strange because the wave function itself is just a function of two Jacobi coordinates in one particular set. So there's apparently no reason to express it in these three sets like this with enlarging the number of different coordinates. Actually, the reason why this decomposition is done is that because for each pair of particles, there will be some correlation that is due to the interaction between the particles of this pair. And so if we write the system as a sum of function like this for each Jacobi coordinate set, then we can build a correlation for each pair using these particular functions. So in general, there would be different functions for each pairs, but here we are considering the three identical bosons. So it's actually sufficient to have the same function chi here for these three terms, and you can easily see that this satisfies the bosonic symmetry of exchange of particles. If you exchange particle 1 and 2 or 2 and 3, etc., that satisfies the symmetry. And so this chi simply satisfies the same free wave equation. And if you make this choice, then of course that's consistent with the fact that the original wave function satisfies the same equation. So so now we can choose a particular set of Jacobi coordinates. For example, this one, we call this small r and small rho. And then we can express the other coordinates of the other sets as a function of this particular choice. And that's something that you can work out very easily by looking at the definition of these vectors by just doing some simple geometry. So it looks like this. And now we apply the two-body condition at short distance between the particles. So when particles I and j come close, the wave function has to be proportional to 1 over rij minus 1 over a. So here the scattering is the same for all pairs because we have identical bosons. And so as we've seen, this is equivalent to saying that the derivative of the small r times the wave function is equal to minus 1 over a r times the wave function for small r. So we just replace this expression of psi in terms of these Faddeev components inside this condition here. So first we have to calculate this derivative of r times psi. So we get this first term, and then we get this second and third term like this. And then for the right-hand side, then we get this expression, just r times this. So this expression is actually for r going to 0. So then we can so it looks like a very long expression, but we can very quickly simplify this expression. The important thing to understand is that, as I said, each chi function will contain the correlation between the one pair of particle. So the first argument of this function chi contains the correction for this particular pair. And as we have seen here, when two particles come close together, the wave function in this zero-range theory diverges as 1 over the distance between the two particles. So this is precisely what is going to be built up in this function chi. So each function chi diverges as 1 over r when this first argument r goes to 0. So if we keep this in mind, we can see where we can safely set r to 0 and where we have to be careful. So for all these terms here, actually we can safely set r goes to 0 because you can see that when r goes to 0, there remains some non-zero vector rho here. So nothing special happens at this particular value of the argument of the first argument of chi. So and so if we multiply by r and then derive by r and taking r equals to 0, we simply get the same function evaluated at r equals 0. So so we just end up with these simple expressions. And the same goes for these terms here. Actually, since they are multiplied by r, they actually vanish when r goes to 0, so we can remove them. But this is not true for this term, for example, because this one has a 1 over r divergence. Okay. Since it is multiplied by r, when r goes to 0, this will go to some finite value. So we cannot get rid of this term when r goes to 0. And this is the same for this term as well. So this has a 1 over r divergence that is cancelled by this term. So this is something that we don't know yet. So we have to keep it. So we end up with this equation. So just to summarize what we've done, we have decomposed the wave function into this Faddeev decomposition with this function chi, and we have an equation now for chi, which is a free wave equation with this particular boundary condition. So I should stress that actually there's only one boundary condition, but we have 3 particles, so we have 3 pairs of particles. So in principle, there are 3 boundary conditions, but because we have a boson system here, all 3 conditions are the same. So actually, the one I get here is actually the same that I would get if I considered another pair or a third pair. So this is the same boundary condition. So there's only one boundary condition in the system, and that actually describes the boundary condition for all 3 pairs. So the next step is to expand this function chi in partial waves, and actually for total angular momentum L equals 0, we can simplify the dependence on these vectors to just a dependence on the norm of these vectors. So essentially that means that there's 0 angular momentum along each of these coordinates. And for convenience, we write it as a function of the distances r and rho divided by these distances. And again, this is the usual form that will simplify the equation, just like we saw for in the two-body case for the partial wave expansion of the two-body wave function. So now, since we have no angular dependence on this, the direction of these vectors, then these Laplace operators, they can simply be expressed in terms of this second order derivative of the distance r and distance rho. So now we'll replace this chi by this expression here. And if we put this expression inside this boundary condition, so you see that we will, this 1 over r will indeed simplify this r factor here, and then you just get 1 over rho. And here we will get this new denominators that are related to this rho. And as you can see, we can multiply this whole equation by a rho. We can simplify it by a rho. So if we multiply by rho, then we end up with this boundary condition for this new function chi naught, and satisfying this equation. So it gets simpler and simpler. Now, the final step is to represent this 2 coordinates, 2 lengths r and rho into polar coordinates. So this is the usual polar coordinates. So we define some radius r, that is just the square root of the sum of the squares of r and rho. And we have some angle to specify the direction in this plane, and we call it alpha. And this is a simplified version of what is called hyperspherical coordinates. That is a general representation of a 3-body or even a few-body system in terms of a single unit of length, a single length coordinates. So this is called a hyperradius, and all the other coordinates are just dimensionless angles that are called hyperangles. So alpha here is called a hyperangle, and R is called a hyperradius. So if we make this change of coordinates, then we find this this equation transformed this way in terms of this R and alpha, and the boundary condition becomes this boundary condition. So now this the conditions that R goes to 0 translates into alpha goes to 0. So the angle, the hyperangle alpha is very small. That's the corresponding boundary condition. The condition when alpha goes to 0. But there's another boundary condition, which is when alpha goes to pi over 2. And this condition is that the chi-naught when alpha is equal to pi over 2 is 0. And this is something that you can see from the fact that we define chi-naught this way. So in order for this function to keep finite values, it means that when rho goes to 0, chi-naught has to also go to 0 to maintain a finite value. So rho goes to 0 corresponds to this alpha equals to pi over 2. So we have this extra condition. And now we can take the unitary limit. So when a goes to infinity. And now what happens is that the two boundary conditions are independent of the hyperradius. When a goes to infinity, you see that this term disappears. So this function, actually, you see that this condition, it just depends parametrically on r's. So there's no explicit dependence on the hyperradius. And also this condition does not depend on the hyperradius explicitly. So that what it means is that the problem becomes separable in the hyperradius and the hyperangle. So that means that you can look for solution of the form chi-naught of R and alpha is equal to some function of the hyperradius times some function of the hyperangle. So we can first look for the solutions corresponding to the hyperangle. So they are given by this operator here. That's the operator that acts on the hyperangle alpha. So it's just the second order derivative, and of course the eigenstates are just this kind of combination of sine and cosine. But remember that we have this this boundary condition here. So in order to satisfy this boundary condition, this should be a sine of so this eigenvalue here Sn times pi over 2 minus alpha, and then you always satisfy this boundary condition that when alpha is pi over 2, this is 0. Okay, so this is the form of these eigenvectors. Yes, so this condition is fine. And now we have to apply the other boundary condition, the one that comes from the interaction. So if we just put this sign expression into this boundary condition equation at unitarity, so this term is 0, then we just get, so we just differentiate here the sign, we get cosine. So we get this equation. And once we have found this, the value of this for this Sn, for this eigenvalue, and that we have determined this eigenstate here, then we can solve the equation for the hyperradius. So it is given by, so the operators for the hyperradius, and now this term, which has this eigenvalue Sn squared coming from this equation. And this leads to, so we can actually rewrite this equation in something that looks more like a more familiar Schrödinger equation. If we consider the function f times the square root of the hyperradius, then we can eliminate this single derivative, and we get an equation of this form. So it looks like a Schrödinger equation, a single dimensional Schrödinger equation with some potential that is Sn squared minus 1/4 divided by r squared at some particular wave number. So this looks like a 1/r2 potential. Now, as you may have recognized already, this equation here is exactly the same that the transcendental equation that was derived by who was that? Faddeev and his collaborator. And as we saw, this equation has one imaginary solution that is given by this S0 is plus or minus I 1.00624. And the interesting thing is that all the other solutions, they correspond to a repulsive potential. But this particular solution, we see that in this equation, it corresponds to an attractive potential. And so this is what we get what we call the Efimov attractive potential. So it's a 1/r squared attraction, and that's quite different from the the usual 1/r squared repulsion, which essentially you can regard it as a kind of generalized centrifugal repulsion. So here we have hyperradius and hyperangles, but if you make an analogy with the usual two-body problem where you have just some distance between two particles and some angle that represent their orientation and their angle related to their angular momentum, their rotation, you would get a term like this, but the coefficient here would always be positive, right? And in fact, if we do all this work that we've done for the three-body problem, but without any interaction at all, we would get exactly the same formalism, except that we will not get this boundary condition like this. We'd get a much simpler one, and the eigenvalues that we would find from this simplified, this more simple equation, will all lead to some positive value here. So that means just centrifugal repulsion or generalized angular momentum centrifugal repulsion. But in the case of these particles interacting with some unitary attraction, that leads to a negative value in one particular channel, and then gives this attraction. So as you can see, this 1/r squared, this actually has this is scale invariant potential, and this you can check that if you have a solution at a particular energy, you can just get the same solution by just scaling the equation by some arbitrary factor lambda. So this is what I do here. Suppose that we have a solution at particular energy minus kappa squared. If you just scale everything in this equation by lambda, you can just rewrite. So you get lambda squared, and you just multiply everything by lambda squared. And you will find that you get another solution for the same equation at an energy lambda squared, kappa squared. So this is well-known properties of this kind of potential. And so then we see that this potential actually has a problem, because without any further boundary condition, we can have any energy as possible. If we have one solution, we can have any negative energy as deep as we want. And so this is exactly the Thomas collapse that we've seen both in the original work by Thomas and also in the Skorniakov Ter-Martirosian's work. But now we have a much clearer picture why we have this collapse. This is because we have this attractive 1/r² potential. So the problem really is due to the fact that we, in the zero approximation, we really neglect what happens at short distance. We just assume that the only role of the interactions is to set two-body scattering lengths. And that works fine for the two-body problem. But we see that sometimes in the three-body problem, that is not enough. And we have neglected too much. And there's actually something else that must be provided by these potentials in the three-body sector. So when three particles come within the range of the interaction B, something happens, and that provides a boundary condition for this 1/r² potential. And once you provide a boundary condition here, then the problem is well defined. So one way to suppose that we have some particular boundary condition, then that will select a particular solution that would be a particular linear combination of the solution of these potentials. And at sufficiently a small distance, you can show that the solutions are of this form. So again, this is the same idea that we saw in this Skorniakov Ter-Martirosian equation. The solutions are of some power law, follow some power laws. So it's just the arguments to the power I(S0) and minus I(0). So one can rewrite it as the cosine of S0 times the logarithm of some quantity lambda that has the unit of 1/length times the hyperradius. And this is what we call the three-body parameter. That's a new parameter that was that has to be introduced, that comes from the short-range physics that has been neglected in the zero-range theory. But we need this new piece of information coming from the short range in order to fix this boundary condition. So that's one way of representing this three-body parameter. Let me see, what do I do here? So if we consider, so now if we replace R by lambda R, then we get this expression. We can separate this here. In order to get the same solution, so now we applying this scale invariance property of this potential, but now using the fact that we have this boundary condition that will put a constraint on the lambda that we can choose. So in order to get the same solution, this quantity has to be equal to pi, modulo 2 pi. And this means that the only possible values of lambda are powers of this quantity lambda 0, which is so if you just invert this relation, you get exponential of pi divided by S0. And as you remember, S0 is about 1.00625. And so if you put that number in, you get something that is close to 22.7. So then what it means is that we replace the scale invariance of this potential when it doesn't have any boundary condition to a discrete scale invariance. So as we should expect in quantum mechanics, then now the levels for negative energy are quantized. They form a discrete set. But interestingly, they form scale invariant discrete sets. So this is called discrete scale invariance. That means that we can go from one state to the other by simply multiplying the energy, and actually all the properties, the wave function also, by just this factor lambda 0, which is just a universal number, just given by just this number 22.7. Now, of course, if you just impose the boundary condition like this, you will not get bound from below, because you could also go down. So this is not enough. In reality, the physical boundary condition will not only fix this linear combination, but it will also set a ground state, right? And that is also to be expected for a physical system. So if we assume that we have a ground state, we can represent it, we can associate it to this three-body parameter by choosing a convention for the starting states, and then we can relate it to this quantity lambda. Yes, so we have discrete scale invariance, so that's the new understanding of the Thomas collapse, and also the spectrum of the system. So people thought that there were probably one or just maybe a few three-body bound state, but actually it turns out there's an infinity of bound state in this potential, as you can see from this property. And actually, it's even more than that, because so far we've been considering the unitary limit, that is when the scattering length is infinite. And indeed, it's not surprising to, as we discussed before in the previous lesson, that we can find scaling invariance at the unitarity. That's because at low energy, the scattering length is the relevant parameter to describe the two-body physics. And when it goes to infinity, then that parameter disappears and there's no more length scale. At least at the two-body level, there's no more length scale. And that's why we obtain a scale invariant system. But actually, somehow this scale invariance also exists away from unitarity in a particular sense that I will explain now. So suppose that we have a solution, chi naught. So this is, remember the equation for chi naught with this boundary condition. But now we have a finite scattering length. So A is not infinite. Then we can make this discrete scaling replacement. So we change R by R divided by this universal factor lambda 0. So what we find is that the equation remains the same, but now we have this new energy. And now the only change in this equation is that we have this now lambda 0 times A. So what it means is that if we have a particular solution, we can find a new solution for a new set of scattering lengths and energy, or binding wave number, which is lambda 0A and kappa divided by lambda 0. So if we now consider the plane determined by these two quantities, from one point in this plane that is a solution, we can find another point that is a solution by simply scaling these two coordinates. So so let me show you. So so before we consider only unitarity, so here this axis is, sorry, is it visible here? Yes. This is the inverse scattering length, 1 over A. So here this is the unitary point where 1 over A is 0, so A is infinite. So you remember here, this is the positive A, negative A, and here for positive A, we have the two-body bound state and diamond. And the first result that we had is that at unitarity, all the energies form a geometric progression that is given by this scaling factor lambda 0. But what we saw in the previous slides is that, sorry, so this is the, yes, okay, three-body continuum particle. And yes, so now we have a three-body system. So above this threshold here, and this threshold, we have actually continuum of states. Here, this is a continuum of states of 3 particles scattering onto each other. And here in this orange region, we have a continuum of states, that is the scattering of one of this dimer, scattering with a 3rd particle. Right, and actually the spectrum for the 3-body bound state is like this. So we know that they have to go through these points, and this is how they behave. And as you can see, there's a correspondence between all these curves. And this correspondence is given by the law we found in the previous slide, that if we have one solution at particular points here, then we can find other solutions by just applying this scaling of the 2 coordinates, this wave number and the inverse scattering length. And so from this property, you understand that each curve is obtained from the other curve by a simple scale transformation centered around this point, 1/a equals 0, k equals 0 in this plane. So this is a remarkable property of the spectrum. The spectrum is actually shows some kind of scale invariance, not only at unitarity, but all around unitarity, even at finite scattering lengths. Yes, so these are the scaling transformation. So in a sense, it's a bit, reminiscent of this Russian dolls that are called matryoshka, that are reproductions of they are kind of self-similar, the production of the same shape, but with different sizes. So that's a kind of interesting analogy with these states. So that's something, again, I should stress, this is something that you see in the spectrum, clearly, the energy spectrum of this Fourier system, but that's also true for the wave function themselves. You have the same properties. So that's why here I represented that the wave function of this trimer here is actually smaller than the wave function of this trimer by the same factor lambda 0. So if you take the wave function for this trimer and you multiply all the distances by lambda 0, you will essentially find the wave function for the next excited trimer. So there are many interesting properties in the spectrum. So the first one is this discrete scale invariance that is through the whole spectrum. The other interesting point is that we actually find Borromean states. Borromean states means that we have n-body states that is bound, even though the n-1 state is not bound, the state with n-1 particles. So here we have n equals 3, so we have 3 particles that are bound, but a subsystem of 2 particles is not bound in this region. So here it is bound, but here it is not bound. So such kind of states are called Borromean, and that is simply in reference to a very well-known symbol that has been used in particular by the Italian family called the Borromeo, and this is the symbol of their family. And this is an interesting symbol that is made of 3 circles that are integrated. But if you look closely, you will see that the way they are integrated is such that if you actually cut one of these circles, one of these rings, you can, for example, this one, you can cut here, you can put it away, and then you will see that the 2 remaining rings actually are not integrated. They can actually freely separate once you have removed one of the rings. So this is a kind of classical picture that is analogous to what happens here in this quantum system, that we have the binding of 3 objects, even though there's no direct binding between 2 objects. So generally, these kind of states are referred to as Borromean states. Okay. And then the third remarkable property about this spectrum is that, as you remember, along this axis, we are actually increasing the interaction, the attraction between the particles. So this is clear from the two-body spectrum that first there's no two-body bound state, and then at some point the attraction is strong enough to bind the two particles, and then the binding energy becomes stronger and stronger. But what happens for the three-body bound states is that they well, first of all, they become bound before the two-body bound state, but then as you increase the attraction, of course, their binding energy increases. But interestingly, you might think that they would keep increasing, and always get and always be larger than the binding of two particles. And that's actually the case in general for the ground states. But you see that for these excited states, what happens is that as you increase the attraction between the three particles, eventually they, is there a question?
Yes, Pascal, I just want to call the attention that Daniele Ferretti made a question.
Okay, so let's,
yeah, it's
okay, anyway, we have an infinite amount of three-body bound states only in the resonant case. Am I right? Yes, that's correct. That's true. There's only an infinite number of states right at unitarity if you consider a finite scattering length. So this particular system has only a finite number of states. For example, here there's only two three-body bound states. That's absolutely correct. But it's interesting to see that that's something that if you just have a fixed system with some interaction potential that is fixed by nature, then you will just find just two states, for example, here, and then you will not see any particular striking structure. But if you actually change the interaction, that's of course something that theorists can do. Then you will reveal this interesting structure that is actually scaling invariant in this plane. So it is quite remarkable. But I agree that indeed, if you just fix the interaction, the scatterings to a particular value, then you just have a finite number of states in general. And it's only when you come very close to the unitary limit that you get an infinite number of a very large number of three-body bound states. So, okay, good. Then, yeah, the last point I was making is that for these excited states, as you increase the attraction between the particles, an interesting and perhaps counterintuitive behavior is that they actually become less and less bound with respect to the two-body bound state, and eventually they actually dissociate. So at this point here, this three-body bound state breaks up into dimer and third particle. So that is an interesting property. Okay. So now again, let's step back a little bit from this, what we understood from this Efimov theory, and understand how it fits into the more general situation. So I like to consider this, again, this is something that mostly theorists can do, although we will see in experiments also, thanks to this Feshbach resonances, we can somehow also investigate this kind of spectrum. So again, I assume that I changed the strengths of the two-body attraction between the particles. As we've seen before, there are different resonances for each two-body bound state that appears in the system. And around each of these, we have this universal region. And when we have this, in the case of these three identical bosons, what we're seeing is that there are, in the three-body spectrum, there are actually an accumulation of three-body bound states, and the number gets larger and larger as we come close to these critical points. So as you can see on these figures, there's a difference between the first resonance, the two-body resonance, and the other two-body resonance, is that here we actually have true bound states. Whereas here in the situation, so as I mentioned earlier, above this two-body bound state, we have a scattering continuum between this two-body bound state and the third particle. So here we have a continuum. So in the three-body problem, what happens is that we have a similar structure to these bound states that occurs here, but now they are embedded into a scattering continuum. So that means they actually occur as resonances, not true bound states. But anyway, the structure can be shown to be very similar to those of the bound states. They are just resonances. And by the way, talking about resonances, I should mention that these three-body states, they actually continue to exist in the three-body scattering continuum at this point as resonances for a certain range of energies, like shown here. I should have mentioned from the very beginning that all these plots are very schematic. They are not to scale. I think, to obtain this plot, essentially I use the exact equation solutions, but for a scaling factor lambda 0 that is not 22.7, but more something like 2. Actually, I think you can see this. So close to 2, I guess. And that's in order to actually see all these states together. If we use the real value of 22.7, this whole spectrum will be stretched in such a way that you will see the ground state, and then this X state will be very, 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 will be 22 times smaller on this graph, and it will extend very far to meet this diamond. So it's very difficult to see. So just for the sake of convenience and visualization, I changed I took an arbitrary value for this scaling factor. But you
Pascal?
Yes?
I just want to call your attention to take a look in the chat. There is a couple of questions.
Okay, sorry. Okay, Johannes. Is there any three-boson 3D non-relativistic system which is characterized by another numerical universal ratio beside 22.7 at A equals infinity? Yeah, well, actually, yes. So as we will see later, this ratio, this particular ratio 22.7, this universal ratio, this is the relevant ratio for 3 identical bosons. But as we will see, there are many other systems where we can have the Efimov effects. Not only identical bosons, we can have indeed mixtures of different kinds of bosons, or even fermions, especially with different masses, and that will change this universal ratio. So, so yes, we can get different values. So in your question was about 3 bosons. So I would say yes if the bosons are different and in particular if they have different masses, then you will get a different universal ratio at A equals infinity.
Yeah.
Okay, and then there's a question. Oh, question from Jasper. Oh, yeah. Hello, Jasper. If the ground state Efimov trimer does not disappear into the atom dimer continuum, do these ground states develop into deeply bound 3-body states as the interaction? Yes, that's right. Okay, before I answer this question, I think Johannes wants to say something. So please go ahead.
No, only if I may. So just to clarify the motivation for my question, I was always intrigued by this number. It seems to be something which is intimately related to 3 bosons acting interacting at unitarity. So the mass is irrelevant. It seems there must be a geometric interpretation. It's something unique to the three-dimensional case. And I was wondering if there is a relation to something else but this transcendental equation which defines it. So if I can express it, let's say, as a sum of Feynman diagrams, as something, a generalized geometric series, this was what I was aiming for.
Okay,
Sorry.
So the first part of your question about the dimensionality, yes, that's for three-dimensional, three identical bosons. And actually, I don't talk about this, but this Efimov effect occurs only, I mean, for identical bosons, it occurs only in 3 dimensions. So if you consider other dimensions, you can show that there's not such scaling invariance. So you don't get any scaling ratio because there's no scaling invariance in the first place. Well, I mean, you can get trivial scaling invariance, not discrete scaling invariance, and then you don't get any scaling ratio. And then your question was about what can it be understood as some sum of Feynman diagrams? Not to my knowledge, and I should say that we are really here in the realm of non-perturbative physics, right? We are very far. I mean, the perturbations here would be down there for weak interactions. Here we really have to sum an infinite number of diagrams to really get these results. This is non-perturbative region of the Schrödinger equation. So I don't know if, I mean, you probably could do perturbation theory to infinite order and get some expression for the solution. Whether you can get a simple expression for this lambda 0 in this way, I have no idea. Maybe, I don't know.
Pascal,
yes.
May I make a comment?
Yes.
Just to broaden a little bit
yes.
This discussion that I think is quite nice. I mean, if you state at integer dimensions 3 and 2, this is exactly what you mentioned. But if you play the game of changing continuously the dimension in your Schrödinger-like equation, you'll be able to have, I mean, still Efimov effect for 3 bosons. I mean, scaling invariance in between. I don't remember. This was derived, I think, by Axel and
by many people. I think also Marcelo also, I think, looked at this problem.
Yes, Marcelo.
Actually, so if you try to go continuously from one dimension to the other, there are several ways to do it. You can use a physical confinement, or you can do some kind of dimensional. I think that's what Marcelo was doing, some kind of wrapping the. But in any case, you have to introduce some length scale, right? That specify how you change you go from one dimension to the other, and that length scale will actually introduce will break the scale invariance at some point. So it means that you will go from an infinite number of states to a large number of states that will eventually converge to a few states that are relevant to the low dimensional limit. So I don't remember the details, but I think in 2D, 1D, you just have a finite number of states.
Two indeed. Yeah,
right.
Just,
So this is how this would occur. But indeed, you would lose the Efimov effect. Or you can, in a sense, you can. Well, if you take your control parameter for this reduction of this dimensionality, this length scale as a new parameter, then I think you can still get some kind of scaling law if you scale that parameter along with the scattering length and the energy. Then you may still. I don't remember the details, but I think you may still have some kind of scaling law like that, at least close to the 3 dimension.
Yes, yes, this is what I have in mind, exactly.
Yeah.
So as you move, at some point there will be, let us say, a critical dimension that just goes, I mean, you do not have anymore the imaginary solution for the transcendental equation. And then you have a continuous scale invariance and not anymore the discrete one.
Right.
Yeah. So this is, I don't know if this is answer also to Yoannis' point or is related to his point, and maybe.
So Johannes, are you satisfied with the answers, or do you need?
Sorry, I was yeah, I'm grateful for the answers, but I'm not satisfied. I was looking for, I understand that it's a non-perturbative phenomenon.
Right.
But it seems, this number seems to be so magic that yeah, its relation may be something to the frequency of the limit cycle it controls, that I was looking for something else. So I was thinking in the direction whether you can characterize it as a transcendental number, as something which comes out of the dynamics of the type of singularities you encounter in this, something along that line. But I understand that it's a very vague question, and I see how it emerges technically, but if there is anything comparable to that, so nothing like that emerges in the, as I know, in the two-body or four-body sector at all, or in those amplitudes and yeah, equations. So the number 3 and this peculiar structure seems to produce this number, but I'm not sure if there is something deep to be said about it besides what you already did.
I mean, in my understanding, there's nothing so deep about it. I mean, it's just a number. That's the number that you get. And again, I mean, for me, the simplest interpretation, I mean, I know you can interpret this Efimov effect as kind of limit cycle. You can regard it from the point of view of renormalization, functional renormalization, and so on. I will not discuss that, but so there are many ways to look at it. But probably I think the most illuminating way is really this effective three-body potential. That is very simple to understand. It means that between your three particles, you have an effective three-body force that is scale invariant because it's 1 over r squared. And the scaling ratio is just simply related to the strength of this potential. That's just this coefficient here. And that happens to be a particular value for these bosons. But as I said, you can continuously change this value by just considering other systems. If one of the bosons has a slightly different mass, then you will change a little bit this number. So I don't think there's something particularly magical about the value itself. It's just the value that you get for this particular case. So I don't know, maybe this is my answer is a bit disappointing. That has been my...
Not at all. Thank you very much. I'm asking this question, I think, a couple of people, and this was very satisfactory answer. Thank you very much.
I mean, if you ever find some, some deeper, meaning or alternative understanding of this scaling factor, then I'd be happy to know.
Yeah, so maybe if you continue to talk about 4-body and 5-body universality, then I might come back to the question.
Okay. That's probably in the next lesson. Yeah. Okay. Then there was a question by Jasper. If the ground state does not disappear into the so that was what I wanted to. Actually, I didn't have time to say yet. What we've seen for this kind of, again, the zero range theory just gives us an ideal theory for this in this limit of close to the unitarity. So that's what is shown by this red dashed red curves. And they are, in the zero-range theory, all these curves are exactly obtained by a scale transformation. But of course, in reality, for a real potential, we have this blue, the real curves with these blue curves, and they only conform to this scale invariance when we are close to this unitary point, right? And we can already see there's some significant deviation for this state. This is all schematic, it's just drawn by hand, but it's just to show you the essence. And for the ground state, typically it follows very roughly, but there's a strong deviation, especially as we go, maybe around here, it's quite close to the zero-range prediction, zero-range theory prediction, but down there, it's markedly different. And Jasper's question was, do they indeed always develop into yes? So I think the generic answer is yes. If you have at least for standard interactions, typical physical interactions, this is typically what you get, that the ground state gets deeper and deeper as you increase the two-body attraction. Okay, so I hope that answers the question. Yes, okay. So are there other questions? Or shall we?
Okay, so maybe you can continue.
Continue, okay.
Okay,
so this is the generic. Okay, so now we can look a bit more about what is an Efimov state after all. So so far, the definition I told you, I mean, the major property I told you is about the relation between two different Efimov states. That is, there's a scaling factor between them, but that doesn't. But if you just find one, it doesn't tell you. You see that's the kind of point of view of theorists, that you can change the interaction, that you can look at this abstract plane where you can see this nice thing. But as we said, in reality, you may have just one state, and then how do you know whether it's an Efimov state or not? So we can look a bit more detailed about the structure of these states. What is the shape of an Efimov state? Well, what you quickly realize when you look at the wave function that we have derived is that in fact there is no definite shape for this three-body system. The wave function is very delocalized, and so the shape is constantly changing. There are high fluctuations, but there is indeed a tendency to form elongated triangles, and this we can show if we start from we express the total wave function as this sum of these three Faddeev components like this. So if we just use all the equation we've used so far, so then we express this guy as a ratio in this function chi-node that depends only on the distances r and rho for each Jacobi coordinate set. And then we went to hyperspherical coordinates with this hyperradius and hyperangles. So then we get this expression. Remember, this is sine alpha, cosine alpha. So we get this sine 2 alpha here for each component. So this in the end, and then we saw that at the unitarity, we actually have a separation between the hyperradius and hyperangle. So we can separate this chi0 into this function f of r, which we can factor at in front of everything, and this function phi 0, which has this expression. So remember, this S0 is imaginary. So if we include the imaginary parts in this sign, then we get a hyperbolic sign function like so. So now we can have an idea of the wave function for this, the total wave function for this three-body system. The hyperradius is actually describes only the global size of the system, whereas the hyperangles actually describe the shape, the geometry. So if we want to focus on the shape itself, we can just concentrate on this part. Yes, that's how I say the hyperradial is the size, hyperangle is the geometry, the shape. And if we simply plot one of these components, So this hyperbolic sign, it looks like this. And so remember, alpha goes from 0 to pi/2. And if we look at the corresponding configuration, this alpha equals close to 0 is an elongated configuration. Alpha equals pi/2 is a flattened configuration, and pi/4 is the equilateral configuration. So we can see that there are fluctuations, so you can find essentially any shape you want. But statistically, if you take a snapshot of the three-body system, you will find you're more likely to find elongated configurations like this. So that's one structural properties that they are form. They tend to form elongated triangles. Now, another question that we may ask ourselves is why do we have in the end this 1/r² effective long-range three-body force, three-body potential? Remember, we started from short-range two-body interactions, and we even used a zero-range theory to derive this. So how can we get long-range from zero-range? This sounds a little bit counterintuitive. Well, the answer is, of course, this attraction is an effective attraction. That's not the real attraction. All the physical attraction in the system are short-range, and it can the way we can understand this effective attraction is to regard it as some kind of mediated interaction. So this is just a schematic picture, nothing serious, but just to give the idea that sorry, maybe there should be an animation here. I'm not sure how to make it work. Okay, maybe I lost that. So sorry, I will just do it by hand then. So there was an animation supposed to show you that as the system, this highly fluctuating system of the shape changes all the time, we can imagine that one of these particles actually come close to another particle, and then it enters the range of interaction, it can interact, and then it can go away and then go to meet the other particle and interact. And this kind of process, so that this can be performed by any of the three particles, of course, but any of the three particles can move between the two other particles. And this kind of motion is actually strongly delocalized because we have a very large scattering length. So you remember we saw for two particles, the wave function extends to very large distance on the order of the scattering length, and that goes far beyond the classical turning point of the interaction. We can actually have a density of probability at very large distance. And so this gives the possibility for these particles to actually travel over a very large distance, much larger than the range of the interaction, and yet provide some interaction that is, in a sense, a kind of mediation of interaction. So that's one way of understanding this 1/r² long-range effective attraction that is the result of the motion of one of the three particles between the two other particles. And that's something that we can actually clarify mathematically when we consider the mass imbalance systems. And in a sense, this is similar to what happens in nature when we have bound states in general. Usually there's something provides a glue between two objects and mediates the force that binds two particles. So this is the case, for example, for atoms in the usual chemical covalent bonding. This is related to an exchange of electrons, right? The electrons keep moving between the two nuclei of the two atoms, and this sharing of electrons is essentially responsible for the binding of the atoms. So of course it's a little bit different because here we have Coulomb interaction and everything, but the general idea is the same, that the mediation of a particle between two other particles can create some kind of bonding. And this is also an idea that we find in the subatomic world for the nuclear force, which can be regarded as the exchange of now virtual particles, virtual mesons. This is the well-known Yukawa picture. So it's just not at the level of ideas. Actually, you can find settings where you can actually go continuously from this Efimov attraction to the Yukawa attraction. Maybe if I have time, I can discuss about it. So there's really some connection between the two, and you can go from essentially an attraction that is mediated by a real particle. Here we have real particles to some attraction that is mediated by something more like a virtual particle. Okay, so hopefully that gives a better intuition about this, why we have a long-range attraction in these short-range systems. Okay, I think I'm done essentially for the Efimov description. What time is it now? Okay, so we have maybe 15 minutes left. So are there questions at this point?
Questions? Thank you, by the way. Very, very interesting.
Is there a question?
Yeah, please.
Yes, Tobias.
Mm-hmm.
Pascal, I just want to put some discussion. We have concentrated in the negative energy region. You mentioned
yes.
resonances, or I mean, when you cross the two-body, threshold, that you have a dimer and a particle. Can you mention what happens a little bit in the scattering region when you are in the presence of this?
Yes, you're right. So I mentioned a little bit here that we have these resonances that actually are the continuation of these bound states. So they occur here and there. So they also follow this scaling, discrete scaling invariance. So they are related to one another by the same. So that means that if you consider the scattering of three particles in this region, you will find the signatures of this discrete scale invariance related to this Efimov physics. There are some works actually, I remember, where they looked at the signature of Efimov physics in the scattering, the three-body scattering continuum. So you have these resonances, and if you look at the form of the T matrix, the scattering three-body T matrix in general, in the sector, I mean, essentially in this whole region, you can find up, even when you're at unitarity, you find some repeating pattern. If you plot any physical value, you will find some repeating pattern that follows this discrete scale invariance. So it really affects everything, not only the bound states, but also the scattering continua as well. And then in this particle dimer scattering, there's also interesting thing that happens here, that at this point you have the trimer breaks up into a dimer and a particle. So you can regard it as a two-body process. This is essentially the point where the scattering length between the dimer and the particle becomes infinite. So again, what we have here is exactly the same as what we have here for this two-body bound state. So now you can regard this as a two-body bound state. And then we have a similar structure to what happens in the two-body case. So in particular, you have some virtual states in this, for this continuum here when you go beyond this point. Yeah, so and again, this repeats itself with the universal scaling factor. So really, this Efimov physics affects not only the bound state but also the scattering states.
But just continuing the curiosity, I mean, in the continuum, people have, I don't know if there is some experiment to evidence, more detail of the scattering amplitudes, not only the position of the resonances, because this is what leads to find the ratio between the two scattering lengths. I don't know if there is some kind of experiment that was able to prove in more detail.
Yeah, you're right. So experimentally, what has been seen more clearly is that these resonances here. So essentially, just the tip of these resonances at low energy. That's the easiest thing to see because that's where we have, I will explain that later, but this is where we have strong losses and we can see some clear experimental signal. And so as I was mentioning, if you sit at unitarity, there is some structure, even though you don't have any resonance, there is some structure of the scattering properties that repeat itself according to this discrete scaling invariance. And there has been proposal to do experiments to see this kind of structure, so a theoretical proposal. And I remember there was actually one experimental report, I think it was from the group of Eric Cornell, I think. Yes, that was Eric Cornell, where they claimed to have seen something. So in their case, they were sitting close to unitarity, and they were measuring something. So that would translate into the densities of their gas, and they claimed that it could. Well, they just showed some result that could see some indication of a scale invariant pattern with measuring the densities at this unitarity point. But as far as I remember, that work was never published in the end. So maybe it was not confirmed in the end. But in principle, there could be some experimental signature also. But I don't think it has ever been reported in publications.
Okay, so other questions? No. I have a slight comment, Pascal, on this,
yes.
this plot, because this plot is so rich that in fact you can probably discuss for hours on this. What you call resonance zero,
yes,
in the domain where you plot that is perfectly fine, it is in between the dimer 1 and dimer 2. But I think that sometime it might go below dimer 1. If you extend the picture very far, you know, to the bottom, okay. But it is, of course, depending on the potential you use, because here there is no universality. But one has to be careful because here, you know, the slope that you indicate that it will remain above, but it might be. So, okay,
that's true. Yeah, I guess that's true. And then probably there's some ambiguity about what you call the resonance zero, because in a sense you can say that this is not. You may say that this has nothing to do with Efimov, and the first term of the series, this one. So it's a kind of arbitrary choice in a sense.
No, but this is clear that you want to show a complete the three-body spectrum. And then of course you have Efimov state, but in addition you have state which are Borromean or non-Efimov or whatever you want, but they might, you know, the ordering of those states with respect to the three-body state might change if you change the potential.
Yeah, actually what you say is very interesting, because indeed it may be possible that this state actually is not, like you said, above dimer 1, but actually crosses dimer 1, so that what happens is that you have some actual bound state that appears from this dimer at some point here. And that's something that is quite typical that we can see. And that's
This is something else. Maybe your picture is maybe better. That from dimer 1 there is something that emerges. one should not neglect the non-Efimov spectrum. Okay, we have a great devotion.
Yes, and actually for certain potentials, so then it really depends on the potentials, and now we're completely outside this universality, but there are some potentials for which actually what happens is that this excited trimer comes very close to the to this dimer and actually doesn't quite touch it, and then it becomes more bound again. So
So
that would be the
This is what
so anything is possible. Yes.
Jean-Marc and Pascal, please take a look in the chat.
The chat.
Yeah.
Chat. Oh, sorry. I am a very bad chairman.
No, but I'm just
Can the Borromean binding of three bodies in the negative scattering length regime also be understood by thinking of two particles interacting via exchange of the third?
Do you answer first or I answer first?
If you want to answer, please.
I can go on. My feeling, I will not say exactly that way. I will say that, suppose that you borrow some third particle and then you increase your mass. And then you get some energy because, you reduce mass with respect to your partner is increased because you have linked temporarily to the third particle. But this is my way of understanding Borromean binding. But it is. But I will agree with that comment. But basically, you exchange not like as you exchange, mesons in the Yukawa theory, but you exchange. This means that the particle is the third particle is associated either to the particle 1 or particle 2, and this increases the mass of the reduced mass of the 1-2 system, and then it becomes bound.
Okay, that's an interesting. I didn't think about this reduction of mass.
Yeah, you increase the mass because you borrow a particle. Yeah.
Yeah. I see. Yes.
But this is, of course, not extremely rigorous.
Yeah, that's right. I mean, this is something that this is a picture that comes afterwards as a kind of rationalization of what we found mathematically. So, but I think it will be probably clearer when we do the mass imbalance case. In that case, we can do the Born-Oppenheimer approximation, and that becomes clearer mathematically. So yes, to answer the question, I think the answer is essentially yes. But again, this is just a picture. This is
what
just
about
a picture.
the last question from Eloisa?
Last question. Yeah. Did you mention if you say with fermions? Yes, Eloisa. Okay. Yes. So actually, I prepared some slides, very basic slides actually, because that question was also asked in the previous lesson. So I should say a bit about fermions. So P wave and fermions, and there was also some mentioning the super Efimov effect. So let me very briefly. Yes, here we are. So very quick ideas. So for what happens, so if we have fermions, so the general answer is you don't have Efimov effect for, at least for identical fermions. The reason is that for if you have fermions in the same states, they have to be, to have antisymmetric wave function. And that means they have to have at least one unit of angular momentum, L equals 1. And so that creates a centrifugal repulsion, and that centrifugal repulsion is 1 over r squared. So it competes directly with the Efimov traction, which is also 1 over r squared. And it actually wins usually over the Efimov traction. Not always, we will see not always, but for identical fermions, it actually wins over the Efimov traction. So the fermionic repulsion is stronger, it's too strong. So there is no Efimov effect. In 3 dimensions. And that's related to the question about P waves. I think other people ask about P waves. So in the lecture, I consider only mostly S wave because that's where we get this zero-inch universality. The standard zero-inch universality. But you might wonder about P wave. So let me quickly show you. So for S wave, we've seen that the phase shift can be expanded at low energy as minus 1 over A, and then we saw, so there's this effective range if we go to the next order. But as we've seen, when the scattering is much larger than the range of potential, this effective range becomes kind of irrelevant. The only thing that matters is the scattering length. And that's something you can see, for example, when you look for the bound state of this, we see that it's just given by the scattering length. However, the situation is different for P waves. So for P waves, we have the following low energy expansion of the phase shift. So the first term is the so-called, so now it has the dimension of a volume. So it's called the scattering volume. And then we have the next term that's proportional to k squared. And there's a coefficient alpha here, which has the unit of inverse length. So this, we might call it the inverse effective range, if we think of range as a distance. And the situation is different from the S wave because, if we look for the bound state, for example, of this P wave bound state, so again we take k equals to imaginary I times kappa, and we have this condition for bound state. But you see that when we so this is what we use to derive the bound state for the S wave. But for the P wave, what happens is actually that the extra term here is not negligible when the scattering volume is very large, because this term k cube is actually smaller than this one at low energy. So the two dominant terms are actually these two, not these two. So in the S wave, it were these two, but for the P wave, these two terms are dominant. And so that means that we find that the binding wave number scales like 1 over the square root of alpha times V. So these two parameters are important. And if we wanted to have something like a Efimov effect, we need to have some kind of scale invariance. So that means that somehow these two parameters should disappear. These two scales should disappear from the problem. That we can do for the scattering volume. We can go to something like a P wave resonance, so when V goes to infinity. But actually this effective range, inverse effective range, it cannot go to 0. There's something called the Wigner bound that is related to the positivity of the probability, the density probability of the wave function, that imposes that this range is this alpha is larger than a certain that 1 over b, so it cannot go to 0. And so some people have conjectured that if these two can go to 0, we would have some kind of Efimov state for identical bosons, but actually that's not the physical limit. For this P wave, what we have is a two-body bound state that is like this. So this is if we plot now the energy, not the momentum, but the energy as a function of 1 over v. So this will be a straight line like this. This is the P wave diameter. So it depends on these two parameters, alpha and v. And if we consider, for example, identical fermions, okay, there's another thing is that this bound state is actually bound state in this kind of potential. So we have the physical attraction, and then we have some kind of barrier here that is due to the P wave centrifugal repulsion, which is absent for S wave. We don't have this kind of centrifugal repulsion. So that means that when the state reaches 0 binding energy, actually it continues to exist as a resonance between this the core and the barrier here, like so. And now if we consider 3 identical bosons in 3 dimensions, some people have looked at what happens. There is no Efimov effect, as I said, for the reasons I explained. But instead you find some, you do find trimers. So there are two kinds of trimers depending on the symmetries of the wave function. They have total angular momentum 1, and the parity can be plus or minus. And interestingly, they have similar structure to Efimov states in the sense that there's a Borromean region, and then they also dissociate into the P wave dimer. But there's not an infinite accumulation of trimers close to this point. So, and the other thing is that these trimers, they are not universally described by this scattering volume and the effective range. So there's no simple universality for these states, unfortunately. You can check this reference, for example, that treats this problem. And maybe if I can conclude, what time is it now? Maybe I should stop. So just very quick word on something that I'm not an expert on. That was just mentioned yesterday, so I thought I could just give very quickly what it is. So everything I said about fermions in P-wave, that's for 3 dimensions. It turns out that if you consider fermions in 2 dimensions, then actually you can get some universal physics. And that has been dubbed the super Efimov effect. So very briefly, so you have this identical fermions in 2 dimensions, then the phase shift can be expressed like this. So now we have a new quantity at low energy that is called the 2D scaling area. That has the dimension of length squared. And presumably this is the only terms that is relevant at low energy, such that when this A goes to infinity, we can get some kind of scaling invariant situation that leads to something similar to the Efimov effect, but a bit different in the sense that we also get an infinite number of states, but instead of the scaling I showed before, that is a geometric progression, we have a double exponential scaling. So, so that makes the spectrum even sparser. The excited states are very, 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 very small binding energies compared to the previous state. So if we have a state En and En plus 1, then the ratio between the logarithm of these binding energies is about 10. So that's a very, very interesting structure of the spectrum that is probably not easy to see experimentally, although it may be easier with particles with different masses. Anyway, so that's this basic result of this so-called super Efimov effect, because we have this double exponential. This is for identical fermions in 2D. And if we try to look at understand it in terms of effective interaction between these 3 particles, that has been worked out also by these people, and we get this kind of 1 over r squared term, but also there's this contribution that is 1 over r squared and this logarithm of r. So r is the hyperradius in this 2-dimensional system, and with this particular shape, then you will get this particular double exponential scaling of the energies. If you want to know more, you can read these references. These are the I think this is the first paper. Yeah, this is the first paper introducing, calling this the super Efimov effect. So I think okay, maybe there's some news in the chat. Okay.
Okay.
So no more.
Thank you very much.
Okay, so I think we are now running out of time.
So you are ready for any question. Very good.
Well, I just thought I should explain a bit more what I didn't fully explain in previous lessons. So here you have a bit more clear explanation, hopefully.
Okay. So no more questions, or maybe we can go to the break, which will be lunch for you and dinner for us, or something like that. Thank you again, Pascal. That's very, very
My pleasure.
And very complete. And so we see you in 2 hours from now, or a little bit less. Okay. Thank you to everybody. Bye-bye.
Bye.
Bye.